Hey everyone. So today I'm going to talk a little bit about the central limit theorem and then also basically develop the theory for extreme value distributions, both the exact type of distribution as well as the asymptotic forms. So with that, let's get going. Okay. So we finished up class last time talking about the central limit theorem, and let me remind you what the basic idea is. The central limit theorem says that if we take the sum of a large number of individually random components, none of which is dominant, that we will get a distribution that tends to the Gaussian distribution as the number of component variables, regardless of their initial distributions, increases. And so this is a really powerful kind of derived distribution. You're basically saying, regardless of the initial distribution of the random variables, if you sum enough of them together, you end up with what looks like a Gaussian distribution for the derived distribution. And let's do an example to kind of illustrate this point. So in this example from the book, we basically consider the random variables xi, each of which have the following probability distribution. So they're essentially PMFs. Let me get my little pointer going. So they're PMFs for each of the xi. And basically, this PMF can take on three values. It's going to be positive 1/2 if xi, little xi equals 1. It's going to be positive 1/2 if xi equals -1, and it's going to be 0 otherwise. And the index here, I, is essentially going to be a positive integer. You can see right away that this satisfies the proper conditions for PMF. That is, if you were to take the entire probability expressed by the PMF, essentially sum these two together, you get 1. And so that makes some sense. Clearly, this is not a Gaussian distribution, right? It's just a PMF with two spikes of 1/2 value of 1/2 each, one at +1 and one at -1. And so what we'd like to show is that if you essentially create a new random variable, which is the sum of a series of these xi's defined by this probability distribution, that the sum of those xi's will tend to a Gaussian distribution. So we basically want to demonstrate that the central limit theorem is correct. And so how do we do that? We basically just define a function g, which is going to relate our new dependent random variable s in this case to the sum of the independent random variables xi, each of which is governed by this probability mass function pxi. And you see that that in this formula, basically, we're normalizing the sum by 1 over square root n. So we get a different dependent random variable depending on the choice of n that we choose. So the bigger the number n, the more random variables xi we're summing over. Let's consider the most simple case because we can actually easily derive the distribution for s for this simple case. And so the simple case is going to be just choosing the smallest number of n apart from n equal to 1, which is uninteresting. All right, so we're going to choose n equal to 2. And so basically our formula for the dependent random variable s then becomes 1 over square root 2, because if you go back, our normalization was 1 over square root of n. And since n is 2, this is going to be 1 over square root 2 times the sum from I equals 1 to 2 of the random variables xi. Recall that each of these xi is going to be essentially will have a probability distribution consistent with that PMF there. And so we can just go ahead and express the sum explicitly. So it's just x1, the random variable x1 plus the random variable x2. And what we'd like to do is derive a new probability mass function for s and compare it to the standard normal distribution to see if S is converging toward the standard normal. So that's kind of where we're going with this analysis. Well, let's think a little bit about the probability distribution for the random variable S. We can use our theory for derived distributions. Basically, remember for PMF, that's just going to be, if we had a formula for G, relating S and Xi and Yj. That's going to be this new derived probability distribution or mass function for S is going to be the sum over all combinations of Xi and Yj when substituted into our formula will equal S. And then we're summing over all the joint probability for those choices of Xi and Yj. Sorry, let me go back. Now we can be a little bit more explicit here. One of the things that if we go back, way back, to the central discussion of the central limit theorem, one of the conditions was that that these components be independent. So some of a large number of individually random components, none of which is dominant 10 to the Gaussian distribution, as the number of component variables, regardless of their initial distributions, increases. So they're individually random components, and maybe it's not explicit here, but also embedded in the central limit theorem is this idea that the random variables have to be independent as well. So we're going to invoke that independence assumption here, and we're going to express the joint PMF for X and Y as the product of PMFs for X1 and X2 separately. So, and remember, basically what I'm doing here is I'm simply basically transcribing our original formula for the derived distribution of a PMF in terms of the formula and the joint PMF for the original variables. And in this case, I'm essentially applying it to our specific problem. In our case, the function g is just going to be equal to this equation for S, which is x1 plus x2 over square root 2. And then, of course, so we're assuming that x1 and x2 are statistically independent. So we can write the PMFs as a product instead of the joint PMF there. So hopefully that's clear. And so basically what we're saying is that the derived or PMF for S, that's PS of S, is going to be equal to the sum of the product of the two PMFs for x1 and x2 evaluated at x1 and x2 such that when we substitute x1 and x2 into this formula, we'll get them equal to S. Okay, so a bit of a brain twister. But let's just kind of work it through and you'll find out that it's not that complicated after all. Let's remind ourselves what the PMF for x1 and x2 look like. Remember, this is what that PMF looks like. It just has two spikes at x equal to 1 and x equal to -1, and it's 0 otherwise. Basically, that means that we're really restricted to a fairly narrow range of x1 and x2 values for which this product is non-zero. And in fact, if you think about it, it's only non-zero if x1 and x2 either equal 1, -1, or a combination of the two. And so we can write that out explicitly here is by saying that that product inside the sum is going to be non-zero basically over the following union of events. When we have x1 union with or intersected with x2, so both x1 and x2 are equal to 1, or x1 is -1 and x2 is -1, so that would be the case where both x1 and x2 are -1, unioned with the case where x1 is equal to 1 and x2 is equal to -1. So we could definitely have a situation like that. In that case, obviously, the px1 would be 1/2 and px2 would be 1/2. Or we could have the case where x1 is equal to -1 and intersect x2 equal to 1. So these are all the different combination of events for x1 and x2 that will give a non-zero value of this product. In other words, that will be the things that the components that we're summing over here. And the next thing that we need to ask ourselves is where would these different events that we're unioning correspond in the S space? Well, that's easy because we have this formula for S. So we just substitute. So in this first event, x1 is equal to 1, x2 is equal to 1. So that's the case where S is equal to 2 over square root 2, which is our first event there in S. The second case is where x1 is -1 and x2 is -1. So in that case, we're going to substitute in, and S is going to be -2 over square root 2. That's the second event in S here. And then this third and fourth event, basically what happens is that x1 is, say, +1 and x2 is -1, so we get 0, so S is 0, or x1 is -1 and x2 is 1, which again, we get 0, and so S is 0. So the last two events for S are going to be 0, 0. So our events in S for these four events in x1 and x2 are 2 over square root 2, minus 2 over square root 2, and 0 and 0. And then the last thing we could ask is what is our derived probability for each of these events? Well, that's easy because if you look at the derived probability, it's basically the sum over all of these different events that we're talking about. And then what we're summing specifically is the product of the PMF for x1 and the PMF for x2. And in these specific events, the PMF for x1 is equal to 1/2, and the PMF for x2 is equal to half. So when you multiply those together, you get 1/4. So the PMF for each of these events is just the same. It's 1/4, 1/4, 1/4, and 1/4. The one thing we note, though, is that these last two events in S are both located at 0. And so basically, we're going to sum over these two 1/4s to get a half, 1/2 at 0. Okay, and so we can actually plot that derived PMF for n equals 2. So I'm just plotting the PMF for S against S, in this case where n is equal to 2. And just like I said, we've got at 0, when S is equal to 0, we've got two events, each of which contribute a probability of 1/4. So we get a total probability of 1/2 or 0.5. And then out here at minus 2 over square root 2, we have a 1/4 probability. And over here at 2 over square root 2, we have a 1/4 probability of 0.25. And then everywhere else we have 0. So this is the derived PMF for the random variable S given an n equal to 2. And look, I mean, it doesn't really look like the normal distribution, but you can imagine it's kind of getting a little bit like the standard normal in the sense that we have a peak. The highest peak is at S equal to 0, and then we have lower probabilities in the flanks. Now, if we wanted to compare this directly to a, say, standard normal PDF, we'd have to change up the units because currently the units of this PMF are expressed in probability, whereas, of course, the units of a PDF are probability per unit, independent random variable unit. And so in order to do that, basically to essentially take this PMF and compare it directly to a standard normal PDF, which is done in this lower graph here, what we have to do is basically take these values of the probability and divide them by the width of the bars. In this case, it's just 2 over square root 2 because our choice of n is equal to 2. And so by doing that, by taking, say, 0.5 and dividing it by 2 square root 2, we're essentially converting the PMF into kind of a quasi PDF because it has the appropriate units. That is, it's going to have the units of probability per unit, say, delta S, which in this case, the delta S is equal to 2 over square root 2. Why is that interesting? Because then we can compare the PMF that we've derived directly with the standard normal distribution, which is shown as the dashed line there. And you can see, yeah, our PMF is beginning to look a little bit like a Gaussian distribution, even for the case where we just have the sum of two of these random variable xi's. And obviously, those xi's look nothing like a Gaussian distribution. They're just two spikes let me go back again. Don't remember exactly. There it is. At 1, x equal to xi equal to 1 and xi equal to minus 1/2 or minus 1. So so that doesn't look anything like a Gaussian PMF. But when you then add the two random variables, each of which is distributed in that way, together, you end up getting something that does look a little bit like a Gaussian, actually standard normal PDF. And so basically, we just did that for n equal to 2. But if it would be a little bit more work, but you can imagine doing exactly the same thing for n equal to 5, n equal to 10, and n equal to 20. And look, lo and behold, this is what we see. We see that basically, as the number of random variables that we sum over increases, the resulting PMF begins to look more and more like the standard normal distribution. And so this is a demonstration of the central limit theorem again, summarizing, what we did was we basically derived the probability distributions for this dependent random variable S based on this formula for G, where each of the xi's definitely was not Gaussian distributed. It was just a PMF with two spikes. And then when we increase the number of those variables that we sum over, we see that the PMF begins to better and better approximate a standard normal distribution. So that's the central limit theorem. Now I want to talk a little bit about another type of derived distribution called an extreme value distribution. And extremes are actually really important. We'll kind of talk a little bit about some of the applications in hydrology, because we're experiencing this winter some really extreme events. So you can imagine, particularly in the face of climate change, that extreme value distributions become very, very important for design and other factors, even human safety. What are extreme value distributions? But basically, extremes are the largest and smallest values from a sample of size n of a known population. And interestingly, these extreme values have their own distributions, which can be derived from the underlying distribution of the population as a whole. And there are really two types of these extreme distributions. There's exact distributions, where we essentially derive the exact form of the extreme value distribution from the underlying or initial distribution. And there's a series of what are called asymptotic distributions, which are valid in the limit of large sample size. And these asymptotic distributions turn out to be very important for practical applications. Okay, so here's kind of a picture of what we're talking about. So we basically have a known population. Let's think about the class project for a second. So, you've been given lots and lots of total coliform or TC data from the beach at Huntington Beach. Say some of you, like each of those individual stations might have 900 or 1,000 measurements over the set of years that I gave you. And you can imagine that what we're doing, and each time we take a sample, is we're just kind of sampling the distribution as it exists in nature, right? So we're trying to approximate or trying to understand what the real distribution is in nature based on some samples that we're collecting. And so we have that known population. I say known, what I mean really is that somebody knows it, maybe God knows it, or some higher power knows it. We would like to know it. But we're assuming that whatever that known population is, it's going to be described by a probability density function, fx of x, and a CDF, fx of x. And so the random variable here associated with this known population is the random variable x. Now we're taking a series of samples from that known population, and we're getting from it a set of realizations. So we take a sample and we take, we measure the TC concentration in that sample. That gives us our value, our sort of, sample of the known population, which we're going to call X1. And then we take another sample and we get X2 and so forth and so on until we get, say, the nth sample. And in the case of some of your stations, maybe that's 1,000 samples. So a little n here would be 1,000. You can imagine that each of these realizations of the known population, little x1 through xn, is essentially a specific value of corresponding random variables x1, x2 through xn. And so that's kind of the setup for the analysis or for the derivation of the exact extreme value distributions. So how does that derivation go? It's actually pretty cool. So basically, the next thing that we do is we define two new random variables describing the extreme values of the sample population that we've collected. And so these are really just derived random variables because we're essentially defining a new, say, function g, right? Where in this case, this new random variable y sub n is going to be the maximum of all of the random variables x1, x2 through xn. So basically, if you had specific realizations for x1, x2 through xn, yn then you would have a corresponding realization for y sub n, which would be the maximum of all of those realizations for x1 through xn. Likewise, we can define a y1, a new random variable y1, which is going to be the minimum of the realizations for x1 through xn. So we've got these two new random variables, yn and y1. And our goal then is to essentially derive probability distributions for each of these, given that we know the probability distributions for the population from which we sample. So we're trying to relate the known probability distribution from the original population to the extreme values that we're sampling in any subset of samples we collect from that population, yn and y1. Okay, so how do we do this? Let's first focus on yn. So that's the maximum, the random variable for the maximum value that we're going to see in a sample of the population. Remember, yn is equal to the maximum of these random variables x1 through xn. Now, we can imagine that if yn is going to be less than or equal to a specific realization of yn, call that little y, that implies that all of these random variables inside the max here also have to be less than or equal to y, right? Because basically what we're saying is that yn is the maximum of all of these. So if yn is less than y, less than or equal to y, that means that x1, x2 through xn have to be less than or equal to y. That makes sense, right? And so basically, given this this relationship, that means that the probability that the yn is going to be less than or equal to y has to be equal to the joint probability that x1, x2 through xn are all less than or equal to y. And now we essentially make two assumptions about these the sort of sample population and the random variables xi. We assume that the xi are all statistically independent. So every time we take a sample, it's statistically independent from all other samples. And we also assume that each of these xi is identically distributed as the parent variate. So if we go back to our picture here, basically what we're saying is that the random variables x1, x2 through xn have exactly the same distribution as the parent population or initial population as it's described here in the red bubble. Okay, so we're going to make these two assumptions: statistical independence and identical distributions for each of these x1s through xn's. And let's kind of see where each of these gets us. So if each of these realizations of or samples that we collect from the known population are statistically independent, that means we can express the probability that yn is less than or equal to y as the product of a series of probabilities. That is, x1 is the probability that x1 is less than or equal to y, probability that x2 is less than or equal to y, and so forth and so on, through xn being less than or equal to y. Okay. And if it turns out that each of these xi's are identically distributed as the parent population, that means that we can replace x1 here with x, x2 with x, xn with x. And so we just have a product of n probabilities that x is less than or equal to y. So we can express then the probability that yn is less than or equal to y as equal to the probability that x is less than or equal to y raised to the n, which is our sample size. And if you think about it, the probability that yn is less than or equal to y, that, my friends, is just the CDF for yn evaluated at y, right? And so basically what we're saying then, and this is our derived CDF then, the CDF for yn evaluated at y is just going to be the CDF for the parent population, fx, evaluated at y, and then raised to the n. So that is our derived distribution for the random variable for the maximum value in a sample of the population of size n. We can also then derive a corresponding PDF for that maximum random variable by just taking the derivative of its CDF with respect to y. And so we then write the PDF is going to be df yn dy. And then we take that derivative over to the right-hand side, and basically we're going to get n times, we're just using the chain rule, fx of y raised to the n minus 1. And then we have to take the derivative of what's inside, which then just gives us the PDF of x evaluated at y. So, so there's our derived distribution for the PDF. The form of the distribution is a PDF, and then also as a CDF here. So we've just obtained our first exact solution or result for the maximum value. And you have to have a little imagination here. So how would you use this in practice? Well, if you had, like in our case, we think that TC data are log normally distributed. So you just plug in that would be fx here. So you just plug in your log normal CDF into this expression to give you the corresponding CDF for the maximum value in a sample of size n. And likewise, for the PDF for the maximum or extreme value distribution, we're going to plug both the CDF for x, in this case log normal CDF, and also its PDF into that formula on the right-hand side. Okay, so that's cool. We can also basically go through exactly the same process to derive an exact distribution for the smallest value in a sample size of n. And so basically, remember, that would be the random variable y1, which is equal to the minimum of all the random variables x1, x2 through xn. And we basically play the game kind of in reverse. So we basically say, hey, if y1 is greater than y, that means that x1, x2 through xn also have to be greater than y. Why is that the case? Because y1 is the smallest of all of those guys. So if y1 is greater than y, that means that x1 through xn also have to be greater than y. We can write that as a probability statement as before. So the probability that y1 is greater than y is going to be equal to the probability that all the x1s through xn's are greater than y. That's the joint probability. And then we just invoke the same two assumptions as before. Every one of those samples from the known population is statistically independent and identically distributed as the parent variate, x. And in that case, when we invoke statistical independence, this joint probability becomes the product of the individual probabilities for each of the x essentially being greater than y. And then when we invoke the identical distribution, then each of these become just identical. So we have n of them. And so then the probability that y1 is greater than y just becomes equal to the probability that x is greater than y raised to the n, that sample size. And from there, it's very easy to derive the corresponding CDF for y1 because we remember that this we can just get the CDF, the probability that y1 is less than or equal to y, as the complement of this probability here. And likewise, we can express the CDF for x being less than or equal to y as the complement of the probability that x is greater than y. And so when we run with that, we end up with the following formula for the derived CDF for y1, derived from the CDF for the parent population x, evaluated at y, and again, given the sample size n. And of course, we can derive the corresponding PDF for y1 by just taking the derivative of the CDF for y1 with respect to y, which gives us this formula here for the PDF of y1. And again, if you knew the CDF and PDF for y1 for the parent population, you could just plug these in, and you would then end up with the derived PDF for y1. Same here for the derived CDF of y1. So that's kind of the basis for the estimating or calculating or deriving actually the exact distributions for y1 and yn. So let's go through an example. This is 4.17 in the book. Consider the initial variate, that would be our known population, with an exponential PDF as follows. So we're going to assume that the parent population is exponentially distributed. And of course, the corresponding CDF is going to look like this. And so we're then asked to essentially derive the distribution for the maximum values we would expect out of a sample population of size n, if we were to sample that parent population with n samples, say. For the CDF for yn, the derived exact solution, we know that CDF is just going to be the CDF for x evaluated at y raised to the n. And likewise for the PDF, we just are going to substitute the corresponding CDF and PDF for the parent population into the right-hand side. And so when we do that, what we find is that the CDF for yn looks like this. So it's 1 minus e to the minus lambda y. I'm just substituting the CDF for the parent population evaluated at y instead of x, and then raising that to the n. And likewise for the PDF for yn, this is what I get here. And again, I'm just substituting both the CDF for the parent population as well as the PDF for the parent population into the master formula. And here's what it looks like. This is actually one of the figures in the textbook. This is what it looks like for the choice of lambda equal to 1.0. And basically what we're looking at is the extreme distributions for the maximum values, the distribution of the maximum values we would expect out of sort of sample populations of various sizes, ranging from n equal to 1 to n equal to 100. And what you see is that as the number of samples that you collect increases, the sort of mode or the most likely sort of maximum value increases. And so, you know, n equals 1, basically, you can imagine that's going to be, the expected value for that is just going to be equal to 1 over lambda, which is 1. So that would be the expected value of the parent population. So if you just have one sample, then the sort of expected value of the extreme is just equal to the expected value of the parent distribution. But as you sample more and more of those samples, the expected distribution or the expected value of the extreme is going to increase. So by the time we sample 100 times, actually the expected value is like 4.5, maybe even closer to 5, if you consider that long tail there. So, so we expect the extreme value to increase the more we sample it. Basically, we see the same exact thing here for the CDF, where you're seeing a shift in the CDF to the right as the sample size increases. We can get a little bit more explicit. I mentioned expected value, so we can actually substitute into or substitute our exact solution for the PDF for yn into the formula for the expected value of yn, which would just be the first moment of that PDF integrated from 0 to infinity, which is the domain of the exponential distribution. And when we carry out that integration, I just had Mathematica do it, we find out that the expected value for yn is actually just equal to, this is pretty cool, I'd never seen this function before, it's the harmonic number of n divided by lambda. And then it gives some conditions which are going to be satisfied, right? We're going to have our sample size is going to be greater than 0, and also the real value of the parameter lambda is going to be greater than 0. And so, so basically I can plot that. I've just created a function here in terms of lambda and the sample size n as the harmonic number of n divided by lambda. And then if I plot that for lambda equal to 1 against n, so this is the number of samples that I've collected from my parent population versus the expected maximum value that I would get in that sample size, you can see that it really rapidly increases for small values of n, and then kind of asymptotes a bit, but it's still rising as we increase our sample size. So by the time we get to 100, a sample size of 100, our expected value is around 5. And that comports exactly with what we observed here in the probability distributions, where it seems like a lot of the probability for n equal to 100 is sort of centered around a value of extreme value of yn equal to 5. Okay, so that really concludes the discussion of exact extreme distributions. Now we can talk about something that's quite interesting and related and actually shows up in the literature quite a lot if you end up studying hydrology or looking at extreme events in some other aspect of engineering, and that's called asymptotic extreme distributions. And basically, asymptotic extreme distributions are mathematical forms of the extreme distribution that are exact in the limit of an infinitely large sample size. And they're kind of general forms which apply to lots of different kinds of underlying parent distributions. And there's actually 3 types of these asymptotic extreme distributions, which show up a lot. They're called type 1, type 2, and type 3. And then more recently, kind of a generalized version of those. Type 1, which is also referred to as a Gumbel distribution, has what's known as a double exponential form. So the distribution actually has sort of layered exponentials, and I'll show you what I mean in a second. Type 2 is the single exponential form, and that is also known as the Fisher-Tippett distribution. And then type 3 is an exponential form with an upper or lower bound, and it's called a Weibull distribution. So you've got the Gumbel, the Fisher-Tippett, and the Weibull distribution. And then the more recent varieties basically are generalizations, which can become type 1, type 2, or type 3, depending on parameter values. And those are called generalized extreme value, or GEV distributions. And, I mentioned that this is of great practical interest. In fact, I just did a quick literature search, and here's a paper in Water Resources Research published in 2010 looking at modeling hydrologic and water quality extremes in a changing climate. So there's a lot of concern about, how the extremes in our water quality and say the stream flow or rain are going to change as climate change. And basically they're using GEV theory to address this issue in this particular paper. Here's another paper that just came out in Geophysical Research Letters, actually, a couple weeks ago. It isn't even out in press yet, looking at time-varying extreme rainfall intensity, duration, frequency curves in a changing climate. And again, they're focusing on using the GEV approach to understand essentially how extremes are changing in precipitation. And I just bring this up because we've kind of personally experienced that this winter, where we're getting essentially one after another 100-year storm, right? And that doesn't make sense. We shouldn't be seeing that many 100-year storms unless something is changing. Okay, so this is what the type 1 or Gumbel distribution looks like. I don't really have anything magic to say about these. I mean, there's a deep theory behind them. We're not going to go into that theory, but basically you just have a CDF and a PDF form of the Gumbel distribution, which depends on two parameters, alpha sub n and u sub n. And so these two distributions are essentially distributions, the CDF and the PDF in this case are CDFs and PDFs for yn, that random variable of the maximum value that you would have in a sample of size n from a known population. The important point to realize is these two parameter values, un and alpha n, which appear in both the CDF and the PDF, can basically be derived from different, explicitly four different parent distributions. So if the parent distribution is an exponential, as we'll see, you get one form of these two parameters or one set of expressions. And if the parent distribution is, say, a normal distribution, you would get another form of these two parameter values. In fact, let's look at that. As pointed out in the book, basically, and remember, the type 1 applies to the case where you have kind of an exponentially declining tail in the parent population. And of course, the exponential distribution is exactly a exponential declining tail. And so that would be a case where the exponential distribution would give rise to a type 1 extreme distribution. And in this case, as shown in the book, and actually even just looking at our previous result for the exact extreme distribution for the exponential, you can show yourself that un and alpha n in this case are is given as follows. Un is the natural log of the sample size divided by lambda, and alpha n is just equal to lambda. And then the corresponding CDF and PDF for the type 1 distributions in the case of the exponential just look like this. I've just substituted these two values for un and alpha n. Let me go back into the Gumbel distributions for the CDF and PDF. And here I'm showing from the book comparison for the choice of lambda equal to 1 of the exact and asymptotic distributions for various choices of sample sizes. And you can see even for n equal to 10 that there's a pretty good match between the PDFs for the exact and asymptotic distributions, but that the match becomes essentially perfect as you go to a sample size of 100 or greater. And same for the CDF version here. It turns out that the Gaussian distribution is also a type 1. You can kind of see that just looking at the Gaussian PDF. I've plotted or indicated here the standard normal distribution. And you can see that as x becomes large, that basically the PDF is going to fall off exponentially, actually like e to the minus x squared, so maybe a little bit faster than exponential. But the net result is that the extreme values associated with the standard normal and the Gaussian in general follow a type 1 or Gumbel extreme value distribution with, it turns out, parameters un and alpha n given by these two expressions here. We haven't derived them. They're actually not derived in the book. They're just transcribed. And then the book points out that if you want to know how those derivations went, you can go to another text. But the other thing I wanted to point out, this is the natural log of the sample size there. So that's what that ln n term is right there. And again, we're just substituting these values of un and alpha n into our CDF and PDF for the Gumbel distribution to get the extreme value distributions for the standard normal. And we can also extend this result to any Gaussian distribution with a mean of mu and a standard deviation of sigma, not just the standard normal, in which case basically the u prime n and alpha prime should be n, sorry, basically are equal to the old un and alpha n that we have up here, just modified by mu and sigma. And so again, this would be the corresponding CDF and PDF for the extreme value distribution for the Gaussian normal. Okay, so let's look at an example. And I really want to try to finish up by thinking a little bit about that TC data set again, kind of bring it all home. So the example here is we're asked to derive the probability distribution for the largest value in a sample from an initial standard normal distribution. Okay, so we just saw in this last slide, we saw the asymptotic distributions, the Gumbel distributions, which are approximate, they're not exact. Now we're being asked to determine the exact distributions for the largest value in a sample of size n. And remember, for the exact distribution, we have an exact result for the derived PDF. It's just equal to n times the CDF for x evaluated at y raised to the n minus 1 times the PDF for x evaluated at y. And in the standard normal distribution, the PDF is just given in the usual way. This guy here, 1 over square root 2 pi times e to the minus x squared over 2. And the corresponding CDF, like I mentioned in class, is just going to be equal to 1/2 times the error function of x over square root 2 plus 1. And like I mentioned in class, this is essentially, when you look at the standard normal tables, this is the function that's being tabulated. So basically, if I take this PDF and CDF for the standard normal and I plug and chug into our derived distribution for the extreme value, I end up with a PDF for yn looking a little bit like this. And so again, what does it depend on? Well, obviously it depends on the value of y, and also it depends on the sample size, little n. And what is y here? It's basically a specific realization for the extreme value. And so we can go ahead and take that formula and plot it. Here I've basically defined that function in Mathematica, and then so this function is defined here as f Gauss as a function of the specific value of the extreme y underscore, just means I can pass that value of y to my function, and also the sample size. So my f Gauss here is just a function of the extreme value y and the sample size n. So that's this this function here, just coded in Mathematica. And then I'm asking Mathematica to plot that f Gauss for various sample sizes ranging from 1 to 10 to 100, where the extreme values are going from essentially 0 to 5. And so what you're seeing then is the plot of that PDF for the extreme value against the specific realization of the extreme value. And you see the distribution for n equal to 1, n equal to 10, n equal to 100. Now, this is really interesting because this is for the standard normal. Of course, the expected value of the standard normal distribution is zero, right? Because it's absolutely symmetrical about zero. But what we're seeing is the expected value or even the distribution of values for the extreme in a sample of size n from the standard normal gets bigger and bigger as that sample size increases. So we're looking at, maybe an expected value of around 2.5 or so if our sample size is 100 for that extreme high or large value, when we sample from the standard normal distribution. So anyway, I just kind of want to make the distinction between the expected value of the population, the parent population, which in this case is zero, versus the expected value of the extreme, the distribution of the extreme values, which in this case is the maximum values, and that ends up getting essentially shifted further and further to the right as the sample size increases. And so what's interesting to do now is actually to compare the exact and asymptotic extreme distributions for a sample from the standard normal distribution. And so now all I have to do is essentially code in Mathematica the Gumbel distribution for the standard normal. And so you'd have to scroll back a couple slides to see it. But remember, we have two parameters, that alpha n and un. And so I've just defined alpha n and un according to the results for the standard normal distribution. And then I have this f approximate Gauss, which is the asymptotic distribution of the Gumbel distribution, again, as a function of y and n. And I'm just plugging in the an and un values here to the Gumbel distribution. And then I want Mathematica to plot a comparison between the exact distribution for the extreme values and the approximate distribution for the extreme values. And so basically I've done that for 3 different sample sizes, sample size of n equal to 2, n equal to 10, and n equal to 100. And you can see that they more or less are similar. There's obviously some differences even out to a sample size of n equal to 100, but they are exhibiting a very similar shape. And the nice thing about the approximate or asymptotic extreme distribution is it's a little bit more mathematically tractable. So I can actually determine the expected maximum value from that asymptotic distribution. And how do I do that? I basically would just take the moment of that asymptotic distribution, first moment. So I take y times that PDF, integrate it over the domain from 0 to infinity. And what Mathematica says when I do that is I get back this explicit expression here involving Euler gammas and gamma functions. But anyway, really, it's just a function of the sample size n. If you look here on the right-hand side, all of the terms involve the sample size n. And so I can plot then that maximum value. So I've just defined this function, maximum value. So that's my expected value of the extreme for using the asymptotic distribution for the standard normal. Plotted that against the sample size. And yep, indeed, you can see that when we get out to about 100, our expected value is about 2.5 or so, which is exactly what we saw. If we go back here, we saw with the distribution that it kind of peaks. The most likely value is sort of around 2.5 or so, with maybe a little bit more probability in the descending tail. So yep, that makes sense. And you can see that expected value for the maximum value increases as the sample size gets larger. All right, so let's bring it all on home, back to the class project. This is something that you could look at in your own data analysis. In the example analysis of the TC data I shared with you on Canvas, there were 615 samples. So this is the example that I went through last time in lecture last. Assuming that the initial distribution of the parent population, that is sort of TC in the wild, is log normal, what is the expected value of the maximum concentration in the sample of 615 samples? So we just basically take that expected value of the asymptotic distribution for the standard normal, and we plug in sample size of 615, and we get back that the expected value for the standard normal variate is going to be 3.13223. So we know that standard normal is going to have this value, that's the expected value, And in the case of a log normal distribution, that standard normal variate is equal to the log transform of TC minus lambda over zeta. So I can solve for log TC in terms of the standard normal, zeta and lambda. And then remember, we had calculated in lecture what zeta and lambda were. So basically, zeta was 2.79 and lambda was 3.42. So if I take my 3.13 for the standard sort of expected value of the standard normal variate, and we multiply it by the zeta I derived before and the lambda I derived before, I get 12.15 for natural log TC. And then if I take e to the both sides of that equation, I get the TC, the expected value for the maximum TC value in a sample size of 615 samples is 189,094. So that's actually quite a bit larger than the 16,000 that we saw was the censored value in that data set, and kind of gives you a sense of how extreme the concentrations can get, at least according to this analysis. So that's it for the online lecture. I hope you enjoyed it, and I will see you in class on, let me see if I can stop this thing. I will see you in class on Wednesday. Okay, talk to you later. Bye.